Hi everybody, welcome to week 8 now, getting close, or week 7 actually. Some more chemistry. We're going to look at nuclear chemistry stuff, so an introduction to how nuclear power works, radiation and things like that. So I'm going to start with this video on Chernobyl, and we'll use Chernobyl as our go-to.
The world's worst civilian nuclear disaster took place when a reactor exploded at the Chernobyl power plant in Ukraine, then part of the Soviet Union. Present-day Belarus received 60% of the initial fallout. The radioactive cloud spread further to cover most of Europe. The Chernobyl nuclear power plant was one of the Soviet Union's most advanced facilities. The first 2 reactors became operational in the late 1970s. The 4th reactor was the newest, going online in 1983. On April 26, 1986, technicians prepared to test the backup cooling system in reactor number 4, but the routine safety drill went horribly wrong. A nuclear reactor is like a giant steam engine. Uranium fuel rods react to produce a massive amount of heat. That converts water into steam, which drives huge turbines to generate electricity. Control rods are inserted in between the uranium to slow the reaction. And it's crucial for cooling water to be pumped around the core to prevent overheating. But as the test began, almost all of the control rods were removed, and technicians lost control of the flow of coolant. Temperatures soared, and extreme heat began to melt the core. At 1:23 a.m., reactor 4 exploded. It spewed 8 tons of radioactive debris into the atmosphere. 115,000 people were evacuated from a 30-kilometer zone around the plant. The battle to put out the fires inside lasted for 15 days. More than 500,000 military and civilian personnel were drafted to deal with the accident and its aftermath. 31 of the initial firefighters and plant workers died within days from acute radiation sickness. The toxicity of the radioactive cloud was equivalent to 400 Hiroshima atomic bomb explosions. Crews hastily built a concrete sarcophagus to encase the entire reactor to prevent more radiation from spreading. Inside, there remained 200 tons of radioactive fuel. The remaining 3 reactors continued to operate due to energy shortages in Ukraine. It wasn't until the year 2000 that the Chernobyl complex was completely shut down. With the concrete sarcophagus crumbling, the international community began to build a new confinement structure for Reactor 4. It stands 110 meters tall, higher than the Statue of Liberty, and it's wide enough to fit a ship the size of the Titanic. At a projected cost of $3 billion, construction is scheduled for completion in 2017. One of Chernobyl's iconic red and white chimneys will be dismantled, and the massive steel dome will slide over reactor number 4. The confinement structure is expected to last for at least 100 years.
Okay, so I don't know if you've watched the series on HBO on Chernobyl, but it explains it very well. And whilst nuclear power is a great tool, it's a very clean energy source compared to coal and natural gas, it does carry with it some risks. But interestingly enough, all of the nuclear radiation that's ever been put out by creating power from nuclear materials is not even 10% of the amount of radiation that's emitted by burning coal each year. So it tends to be much safer than others, but there's a big fear about nuclear power. If you look at that with Chernobyl in the 80s, and then we had what was the word? Fukushima in 2009, I think it was, where the tsunami overwhelmed the seawall. And then we have radioactive water pouring into the sea. So it does have its consequences. It is clean energy. It is relatively cheap, but we are still dealing with the nuclear field. So we'll go through the basics of what is the nuclear field. So the mass of uranium or plutonium in Fat Man, which was one of the bombs that was built to be dropped in World War II, atomic bomb, is tiny. To have an explosion that size with a traditional explosive, it would need to be thousands and thousands and thousands and thousands of tons. Whereas tiny little mass of nuclear fuel, you split that atom into two, it releases particles that will go through, that hit the next atom, which then splits and starts this runaway chain reaction. And in Chernobyl, unfortunately, they let the reaction get to a point where they couldn't bring it back. It ran away, and there was no way to stop it from going so hot that everything just melted. So, nuclear bomb, very small amount of fuel required to make a blast that size. That would level city blocks and kill tens, if not hundreds of thousands of dropped on a city. If you have a basement in your house, you are exposed to more radiation than the average person, because the radon exists in the bedrock underneath, and exists also in the concrete and some of the pylons that get drilled into the bedrock. And radon is a radioactive element. It's a gas. It's odorless, colorless, doesn't taste like anything. You can't see it, but we are exposed to it every day. And there's a lot of fear around radiation. Radiation is really bad for you, depending on the type, but also we're all exposed to a large amount of background radiation every day. If you look at how much, I think even the person that works in a nuclear power plant, being very high exposure rates, they still don't have that higher risk of radiation-related illnesses as the average person. So there is a safe limit. X-rays, MRIs, CAT scans, PET scans, all expose us to radiation, but they're all within safe limits, provided we don't get too many of them in a 12-month period. So we're looking at, you might have heard the term radioactive isotopes. And the isotopes, so this is the chemical symbol. And the number of neutrons and protons differs between the isotopes. So there's not just like hydrogen, there's 3 different naturally occurring types of hydrogen. And they differ in the protons and neutrons, which is bound together by this nuclear strong force within the nucleus. So the strong force is the technical name that holds them together. So isotopes, atoms have a given element with the same number of protons, but they differ in their neutrons. The neutron number is what makes them unstable. So if there's too many neutrons in the nucleus, the atom is unstable. So you've got protium. So these are all the isotopes of hydrogen. Protium deuterium, and tritium. They're all hydrogen, they just have different numbers of neutrons. So hydrogen as it exists normally is just a proton. So it exists mostly as protium. Deuterium is one proton and one neutron. Tritium has two neutrons and one proton. If we look at the numbers, this number here is the total of the protons and neutrons. And this is the number of protons, which you can get from taking this number from this. Carbon also has radioactive isotopes, so carbon-14 dating. I don't know if you've heard the term carbon dating. But you can measure how much carbon-14 and carbon-12 there is. So carbon-14 over time breaks down to carbon-12. So carbon-13, carbon-12. And if you know the ratio between the two, you can calculate roughly how long or how old that particular, use it for newish fossils. But it's only really effective for dating maybe back to 40,000 years at the most. So, the radioactivity refers to elements that are unstable. And by unstable, they release these particles from the nucleus. What happens? Those particles, depending on, there's three different types, but they will interact with, so if you're looking at humans, they will interact with DNA, biological molecules, and start to break them down. When they hit other atoms, then they cause those atoms to be unstable, and that's why we get that nuclear chain reaction. So, like most things in science, the discovery of radioactivity was completely by accident. Uranium has a really strange color. It's like a greeny yellow glow. And it emits radioactivity. So they were trying to take photos. You guys are probably too young, but we used to have cameras that had a film on them. You didn't get to see the photo straight away. You had to develop the photo, and you couldn't see it for however long. It may have been 2 weeks. It used to take sometimes. When they developed overnight and the same day, the world went mad. You take a photo and you can see it that same day. But the uranium radioactivity was actually breaking down the film or fogging it. So it's Henry Becquerel is said to be the father of radioactivity. But then you also had Mary and Pierre Curie. If you're a young female that you want a scientist to look up to, she is definitely the one. She has two elements named. She named two elements on the periodic table, and that's also an element named after her. So, for a woman to win the Nobel Prize in the early 1900s was out of this world. Like that just didn't happen. But such was the size and the significance of her discovery. Obviously, she won it in 1903 with two men, and then in 1911 she won the Nobel Prize in chemistry again. Oh no, she won the physics first, and then the Nobel Prize in chemistry. Again, even in 1911, to have a solo female winner of the Nobel Prize in chemistry or physics, that's unheard of. If you had said to anyone then it was going to happen, probably laugh though. So, yeah, she was incredible. Unfortunately, like most of these guys, in the early days of radiation, they didn't understand it was dangerous. And a lot of them, unfortunately, succumbed to cancers that we know are caused by radiation. I think she died in her 40s. I don't think she lived very long. These guys were playing around with radium and all these radioactive compounds without any protection. They didn't know it was bad. They didn't know it was dangerous. And not all radiation is particularly dangerous. So we have alpha, which emits a helium nucleus. It is the lowest energy, so it's not really that dangerous. Beta, and it's positively charged. Beta basically emits an electron. It has a negative charge. And then we have gamma radiation. This is the bad. This is the kind of radiation that, I don't know if you've ever, but in high enough doses, it will burn the skin off your hand. So the guys that responded to Chernobyl, they're picking up the graphite, wondering what it was, and that stuff it sits next to a radioactive reaction, nuclear reaction, and they picked it up and it burnt the skin straight off their hands. Normally, radiation exposure is long term, and you get a damage accruing over time. The gamma rays damage biological molecules, so the DNA, the proteins, the carbohydrates, and as the dose goes up, the damage happens quicker and quicker and quicker. Back in, I don't know if any of your parents were old enough, maybe not, but back in the 1960s and 70s during the Cold War period, where the US and the USSR at the time were seeing who could build the most powerful nuclear weapons and threatening each other. And thankfully they didn't. There's a concept of mutually assured destruction, which if one country launched one, then the other country has nothing to lose by launching 10 back. And then the other country would launch 10, and it would be a nuclear holocaust. But we have a thyroid gland in our neck, and it takes up iodine and uses iodine as part of its messages, or the hormones that it gives out. And when the nuclear bomb goes off, it releases radioactive iodine into the atmosphere. So the body will take that up and use it and start putting it in your throat. So what they used to do was they would give you regular iodine to saturate your body. And it would suddenly, if there was a nuclear blast, you wouldn't end up getting radioactive iodine in your thyroid. Your body would already have enough salt to take it. But that produces those gamma rays. So once it's in there, the rate of thyroid cancer around Chernobyl and around other places where there's been nuclear disasters is many, many times above what is normal. So we have, the first kind of radioactive emissions is alpha particles. And that is 2 neutrons and 2 protons. So, but they're not that bad. I mean, it's still radiation, but it's not that bad. It can only travel a few inches, and a sheet of paper or your clothes will stop it. It has a positive charge, or a 2 positive charge, because it has 2 protons. So we have 238 uranium. We lose 2 protons and 2 neutrons, and it becomes thorium. So if we look at the periodic table, uranium is 92, 93, and you've got lead, which is further back. I can't remember the exact number. But each time lead decays like this, it goes back an element. Sorry, every time uranium decays, it loses 2 protons and 2 neutrons. And it keeps doing that until it gets back to lead, which is where it's stable. So, and it does that because it has a really unstable nucleus. It has an atomic number greater than 83. Pardon me. Atomic number greater than 83, so its nucleus is large and unstable. It loses 2 electrons, sorry, 2 protons and 2 neutrons, and the nucleus becomes smaller and more stable. So each of the radioactive elements is just trying to get more stable. That's why they are radioactive, because they are unstable. If we look at beta particles, it's when we eject electrons from the nucleus. So the neutrons undergo a decay and they become negatively charged. And they have the same mass and charge as the regular electrons. The electrons are ejected from the nucleus when the neutrons decay. We can stop them with aluminium foil or wood. So they're not particularly dangerous. I mean, it's still radiation, but it's not going to do a huge amount of damage. So they lose a negative charge and they become positively charged. Thorium decays to protactinium. So it loses a minus charge and becomes positively charged. And this is the dangerous one. This is the bad one, for lack of a better term. So the gamma rays are electromagnetic waves. They don't have a mass and they don't have a charge. The only way to stop these, you can see in Chernobyl, they built the sarcophagus made of concrete and steel and lead. And the reason that the one they built is now breaking down is because the radiation has destroyed it. And that's why the entire world has spent a small fortune on trying to encase Chernobyl. So, polonium decays to lead. Gamma decay is different because it doesn't technically change the element. The element is still there. So we still, in the beta, the electron is emitted from the nucleus during this decay. So you see the radiation source. The alpha waves can be stopped by paper. The aluminium stopped by the beta. And fortunately, gamma requires lead. So gamma rays can go, they will just go through you. And they're the ones that attack the biological molecules. And the ones that cause the damage. So We have rays of light, which are not very penetrating. They're absorbed by the skin. X-rays, slightly more penetrating. And gamma rays will just can effectively go straight through. And they're absorbed by different biological molecules. So if we have a negative charge over here and a positive charge over here, then the positive helium nuclei, so the alpha decay, will go this way. Number 2 would be gamma radiation. It's not affected by the magnetic field because it doesn't have an electrical charge. Whereas beta decay would go to the positive side because they are electrons. So you can see another way here, if you have radium surrounded by lead, but we have a tube, we'd have alpha particles would go one way, the beta particles would go the other way, and the gamma rays would not be affected by the magnet. So there's another concept we can talk about here. We have nuclear stability, which is how stable is the nucleus, and then the half-life. And I'll explain both those concepts. So the nuclear stability depends on the neutron to proton ratio. If that number is too high, the nucleus is unstable, and anything above about element 83, with some exceptions, are unstable and thus radioactive. So the further you get from this line, the more and the worse the radiation emission becomes. So if you have too many neutrons and not enough protons, as you can see here on this graph, the radiation increases, or the emission of the radiation increases. So this is what happens. This is why we have this decay. The nucleus isn't built to handle that. For some reason, in the creation of the universe, that these elements were created. So if there's too many neutrons, we know the neutrons decay into electrons, and then they are released as electrons. So N14. Oh, sorry. So nuclei with the atomic number greater than 83 are radioactive. There are a couple of exceptions to that rule, but for the most part, they are radioactive. And this is something that some people tend to struggle with, is the half-life. So if I have, I'll explain it when you see the graph. So this, it's basically, in year 0, they have, let's call it 1,000 radiations. Let's get really technical. In 10 years, if that's 10 years of their half-life, they'll only have 5,000. And in 20 years, they'll have 2,500. And then in 30 years, so every time the half-life happens, you lose half. Uranium-238, which is often used in, well, used to be used in nuclear power and nuclear weapons. It's 4.4 billion years to become not radioactive. So once an area is contaminated, it's pretty well contaminated forever. Uranium-235, a more common in nuclear fuel, 7 billion years. Radon, which is a gas carbon-14, and they all release different kinds of radiation. So after one half-life, there is half of the original sample left. So in if you've got a gram of uranium-235, in 7 billion years, you'll have half a gram of that and then half a gram of lead, whatever the next decay product is. So after 2 half-lives, there's half of the original half, so 1/4 of the original sample. And then after 3 half-lives, there's 1/8, 4 half-lives, there's 1/16, 5, there's 1/32, so on and so forth. So at 0 time here, then at 1 half-life, you've got the original amount divided by 2, 2 half-lives, you've got the original amount divided by 4, 3 half-lives, you've got the original amount divided by 8, 4 half-lives, 16, 5 half-lives, 32, so on and so forth. And that's why nuclear accident can have such a devastating effect, because of how long the area will remain contaminated unless you physically pick it up and move it. They're trying to what's the word? Make the farmlands around Fukushima safe. So they're quite literally picking up the topsoil and taking it away. It's the only way to remove that radiation at this point in time. In Chernobyl, all of the leaves that were on the ground, so close, really close to the plant, all the leaves that were on the ground are still there. Because all of the organisms that break it down were killed by the radiation and have never been replenished. And if a large forest fire were to go through the forests around Chernobyl, it would blanket the world in a cloud, not the world, probably Europe, in a cloud of radioactive smoke. Because you couldn't go in there and fight it because it would be too dangerous. But if it's burning through all the trees and all the undergrowth, it's just saturated in radiation. Once it burns, it will go up into the sky. So we have 100 grams of radioactive C14, and the half-life is 5,730 years. How many grams are left after 1 half-life? So you would simply halve the original amount. How many grams are left after 2 half-lives? Then you halve that amount again. You halve that the second amount.